Hello, my name is Ali Kararudi and I'll be talking to you about search algorithms in C++ during this video. The most important operation that can be performed on a list is the search algorithm. Using the search algorithm, you can do the following. Determine whether a particular item is in the list, if the data is especially organized, like sorted. You can find the location in the list where a new item can be inserted. You can find the location of an item to be deleted. The search algorithm's performance, therefore, is crucial. If the search is slow, it takes a large amount of computer time to accomplish your task. If the search is fast, you can accomplish your task quickly. Analysis of the algorithms enables programmers to decide which algorithm to use for a specific application. Before exploring these algorithms, let me make the following observation. Associated with each item in a dataset is a special member that uniquely identifies the item in the dataset. For example, if you have a dataset consisting of student records, then the student ID uniquely identifies each student in a particular school. This unique member of the item is called the key. The keys of the items in the dataset are used in such operations as searching, sorting, inserting, and deleting. For instance, we can search the dataset for a particular item. We compare the key of the item for which we are searching for with the key of the item in the dataset. When analyzing, searching, and sorting algorithms, the key comparisons refer to comparing the key of the searched item with the key of an item in the list. The number of the key comparisons refers to the number of items, the key of which is being compared with the key of the item in the list. So the first algorithm to look at is sequential search. Sequential search also is called linear search. The sequential search works the same for both array-based and linked lists. The search always starts at the first element in the list and continues until either the item is found or the entire list is searched and the item does not exist in the list. Because we are interested in the performance of the sequential search, which is the analysis of this type of search, for easy reference and sake of completeness, I will consider that if we find the item in the list, we will return the index of the item. And if we don't find the item, we will return -1 so that it signifies that the item is not found in the list. Note that the sequential search does not require the list elements to be in any particular order. So let's take a look at this template. So what we have in this template is we are looking at a list named list, okay? And we're looking at different locations in that list. For the indexes, we're using location. And we define the found, a Boolean found, which we set it to be false. As you can guess, when we find the item, this Boolean found is going to turn to be true. And we initialize location to be 0 because we want to start from the beginning of the data structure, which in this case is a list, okay? So what we do is we create a loop, which is this while, okay? And as long as the location is less than list length, so basically this means we're going to go from 0 all the way up to the last item in the list, and the not found is true. Remember at the beginning not found was false, so now we check to make sure it is not false. So if we find the item, we're going to turn found to be true. You're going to see that later in this code. And then not found is the opposite of it, which is going to be false, and that is going to break this loop. Within the loop, we check and we see if the list location equals item. Consider item is what we're looking for, okay? And it's being passed over here to this template function. You see that? Good. So If that is the case, meaning we found the item at the list location, so we set the found to be true, which means this not found is false, which means this whole statement now is going to be false, and while loop is going to be broken. Else, if that is not the case, we do location plus plus, which is going to do another iteration of the loop. So that's the control part. Then in the operation part, we check if found is true, meaning we found the item. What we do is we return the location, which remember location is the index of that item within the list. If not, we're going to return -1, which basically tells us we haven't found any item in that list. Okay? So now let's talk about the analysis of this type of search, okay? I want to analyze the performance of the sequential search algorithm in both the worst case and the average case. Let's look at this. The statements before and after loop, so we're talking about these guys over here and the end, they only execute once and hence require very little computer time. Remember, if something is being executed only once, considering the speed of the computers nowadays, we really don't consume that much speed of the computer, right? So what really makes the big difference is what is being repeated times and times and times, and considering how many times this repetition actually happens, which is time consuming, right? The statements in the while loop are the ones that are repeated several times. For each iteration of loop, the search item is compared with an element in the list, and a few other statements are executed, including some other comparisons. Clearly, the loop terminates as soon as the search item is found in the list. Therefore, execution of the other statements in the loop is directly related to the outcome of the key comparisons. Also, different programmers might implement the same algorithm differently, although the number of key comparisons would typically be the same. The speed of a computer can also easily affect the time an algorithm takes to perform, but of course, it does not affect the number of key comparisons required. Therefore, when analyzing search algorithms, we count the number of key comparisons because this number gives us the most useful information. Furthermore, the criteria for counting the number of key comparisons can be applied equally well to the other search algorithms. Okay? Let's talk about this in mathematical language. Suppose that L is a list of length n. We want to determine the number of key comparisons made by the sequential search when the list L is searched for a given item. If the search item is not in the list, let's see what happens. We compare the search item with every element in the list, actually making n comparisons. This is really an unsuccessful case, and as you notice, it has the maximum number of comparisons, which is n, which is sometimes called as worst case. Suppose that the search item is in the list. Then the number of key comparisons actually depends on where in the list the search item is located. If the search item is the first element of L, we make only one key comparison. Lucky us, right? This is the best case. On the other hand, if the search item is the last element in the list, the algorithm makes n comparisons and actually does the worst case again. The best and worst cases are not likely to occur every time we apply the sequential search on L, right? So it would be more helpful if we could determine the average behavior of the algorithm, which is best case and worst case divided by 2 to get the average, right? That is when we need to determine the average number of key comparisons the sequential search algorithm makes in the successful case. To determine the average number of comparisons in the successful case of a sequential search, We first consider all possible cases. Then we find the number of comparisons for each case, and then we add the number of comparisons, and then we divide them by the number of cases. If the search item that we call a target is the first element in the list, one comparison and only one comparison is required. Then if the target is the second element in the list, we need two comparisons. Similarly for third, fourth, fifth, and so on. So if the target is the kth element in the list, k comparisons are required. It's very simple to derive. So we assume that the target can be any element in the list. That is, all list elements are equally likely to be the target. Suppose that there are n elements in the list. So if you think about it that way, then we have 1, 2, 3, 4, all the way to n comparisons depending on where the element is. And to average it out, we have to divide it by n. So this is where this formula comes, right? Number of possible comparisons divided by number of items. It is known that 1 plus 2 plus whatever plus n is equal to n times n plus 1 divided by 2, right? So we kind of like write that part in this. So as you can see, this part, 1 plus all the way to n, is now this part, n times n plus 1 divided by 2. And then we have this division by n, which we put it down here. Now we get rid of n by n, and the result is going to be n plus 1 divided by 2. This expression shows that, on average, a successful sequential search searches half of the list. And it actually makes sense. Think about it. Average of going through everything in the list is nothing but what? Half of the list, right? But we mathematically proved it over here. Okay? It just follows that if the list size is, let's say, 1 million on average, the sequential search makes 500,000 comparisons. As a result, the sequential search is not really an efficient search for large size of data, which is a very good reason to use a different type of search algorithm called a binary search, which is very fast. A binary search can be performed only on the sorted list. It's very important to understand. In order to use binary search, your list must be sorted, or you have no other option but to go back to sequential search. We assume all the lists that we talk about hereafter are sorted. Later in this video, when we do the code, we're going to remind you this again. So the binary search algorithm uses the divide and conquer technique, meaning that first, the search algorithm is looking at the item to search for, and the search item is compared with the middle element of the list. If the search item is less than the middle element of the list, we restrict the search then to the first half of the list. Otherwise, we search the second half of the list. Okay, let's talk about this a little bit more with an example. So consider we have a list of size 12, okay? And the numbers in this list, as you can see, are sequentially ordered, and it's a sorted list. The task here is to figure out if number 75 exists in this list or not. So as we said, the first step is to compare that item, which in this case is number 75, with the item in the middle of the list or list with the index 5. So as you can see, 75 is greater than 39. So logically, because this list is sorted, we don't expect the item to be here in this lower range. So what we do is we change the restricted area that we search for to all the items greater than 39 over here, right? And therefore, our list is going to be starting from list index 6, go all the way to list index 11. Now we have a new list, which is half in the size, to look at and look for the item. And then This time we're going to again look and compare it with the item in the middle, which is going to be 66. And in this case, then we're going to go ahead and get restricted to these three items. And then again, we compare with 89. And because 75 is less than 89, now we'll look down to this item. At this point, this new list has only one member, and that one member is 75. And we already have found the item that we have been looking for. So as you can see, this process gets repeated, and each time the size of the new list is going to be half the size of the original list. So let's take a look at the code that goes with this algorithm. So in our template, we pass a list, a length, and an item to search for. So we usually define first to be 0. Remember, this is going to be an index, right? Last, which is another index, is equal to length minus 1. The reason for which is we start counting from index 0, and therefore length minus 1 is going to be the index for the last item. And then because our algorithm needs to look at the middle item, we'll define a mid, which is basically the index of the middle item in this list. Like the algorithm we had for linear list here, we set a found, set it to false. We already explained this. So the loop control this time says as long as first is less than or equal to last, and remember last is the last item, and the item is not found yet, continue the list. So this is the part that we iterate. So the first thing we do is we find the mid, which is going to be the average of first and last. And remember, this is going to be an integer division. So if the size is, for example, 11, the result of dividing 11 by 2 is going to be 5. So we go to the fifth item no matter what. So if list in the middle, which is the middle item, is equal to the items, of course, found is going to be true, meaning we found the item. Else, if it is greater than, notice that if the list middle is greater than item, that means item is going to be where? It's going to be in the half part of list, which is less than middle. Therefore, we set the last index of the new list to be the middle minus 1. So basically, this is where we set the new list. Notice that we didn't change first, we only changed last. But if this is not the case, meaning item is greater than the middle item in the list, in that case, our search criteria is going to be the greater half of the list. So we don't need to touch the last, therefore we only touch the first, which is going to be mid plus 1. So as you can see with this control over here, we are basically deciding which half of the list is going to be the next half to search for and find the item in. And after this, loop is done. If the found is found, we return mid, which basically at this point is the item. And if not, we return minus 1, which signifies that the item was not found in the list. In general, suppose that L is a sorted list of size n. Moreover, suppose that n is a power of 2, that is, n equals 2 to the m. For some non-negative integer n, actually. After each iteration of while loop, about half of the elements are left to search. That is, the search sublist for the next iteration is half the size of the current sublist. For example, after the first iteration, the search sublist is of the size about n divided by 2 equals 2 to the power of m minus 1. It is easy to see that the maximum number of the iterations of the while loop is about m plus 1. Also, m equals log 2 of n. Each iteration makes two key comparisons. Thus, the maximum number of comparisons to determine whether an element x is in L is 2 times m plus 1, which is actually equal to 2 log 2 of n plus 1, which brings us down to 2 log 2 of n plus 2. In the case of successful search, it can be shown that for a list of length n, on average, a binary search makes 2 log 2 of n minus 3 key comparisons. In the case of an unsuccessful search, it can be shown that for a list of length n, a binary search makes approximately two log 2 of n key comparisons. Just as a problem is analyzed before writing the algorithm and the computer program, after an algorithm is designed, it should also be analyzed. Usually, there are various ways to design a particular algorithm. Certain algorithms take very little computer time to execute, while others take a considerable amount of time. Usually, in an algorithm, certain operations are dominant. What we do is we look at those dominant operations in order to figure out the actual performance of an algorithm. Similarly, in a search algorithm, because the search item is compared with the items in the list, the dominant operations would be comparison. That is the relational operation. Therefore, in the case of a search algorithm, we only count the number of comparisons. Within the same concept, whenever it comes to algorithm study, we only consider the dominant operations, not all the operations. Suppose that an algorithm performs function of n basic operations to accomplish a task, in which n is the size of the problem. Suppose that you want to determine whether an item is in a list and that the size of the list is n. To determine where this item is, or whether if the item actually is in the list or not, there are various algorithms. However, the basic method is to compare the item with the item in the list. Therefore, the performance of the algorithm depends on the number of these comparisons. Thus, in the case of the search, n is the size of the list, and function of n becomes the count function. That is, f of n gives the number of comparisons done by the search algorithm. To generalize this, let f be a function of n. By the term asymptotic, we mean the study of function f as n becomes larger and larger without bound. We say the f of n is big O of g of n, written f of n equals big O of g of n, as you can see right over here, if there are constants c and n0 such that Fn is less than or equal to Cgn for all n's greater than n0. As I said earlier, big O notation helps us understand and study the growth of f of n with the growth of n. So let's take a look at this graph pretty quick. So as you can see, we have functions like log2 of n, which they don't grow quickly, they're slowly growing over here. And we have functions like n to the second that are growing pretty fast and they're going all above. So as you can see, when you see the big O of an algorithm, you can decide which one is a faster, which one is a slower, which one grows slower and therefore is a faster algorithm, which one grows faster and therefore is a slower algorithm. This table shows how certain functions grow as the parameter n or the problem size grows. Suppose that n doubles, so then the size of the problem grows twice. As you can see, log2 of n function just goes up by 1, and log2 of n goes by 2, n2 goes by 2, and then 2 to the n goes to quadruple, go to 4 times. As n grows, as you can see here with log2 of n, we slowly grow, right? 2, 3, 4, and 5. With n log 2 of n, as you can see, when n grows, we go faster, faster, and faster. N to the second has even a faster growth rate. As you can see, it goes to 16, 64, 256, 1024, and so on and so forth. And then the worst of them is 2 to the n. As you can see, it goes 16, 256, and so on and so forth. And just do a comparison between when the size of the problem goes 32 and here with log 2 of n we have 5 and 2 to the n we have a huge algorithm. Looking at the time spent over here on this slide and compare it with the number of iterations your algorithm needs to go through may give you a better understanding of how important it is studying the big O notation. So this table shows the time for FN instructions on a computer that executes 1 billion instructions per second. So if you see, when you have 10 instructions to be processed, the difference between these is not really that big of a deal. So you may not even feel it. But if you just go up a little bit, like go to 50 instructions, look at the difference between when your big O is N, which is 0.5 microseconds, compared to 2 to the N, which is 13 days. And you just double from there, and this algorithm is going to take you 4 times 10 to the power of 13 years. So you're not going to be alive to see the result of this calculation. And this is a fast computer. We are talking about executing 1 billion instructions per second. And you can see the difference between the algorithms over here, from tenths of a microsecond to 10 microsecond over here, right? So we usually use this tool to figure out which algorithm is a superior one from the perspective of performance. The other matter to be considered in calculation and analysis of big O notation of an algorithm is that we usually only look at the highest effective parameter. Let's do this comparison. Over here, I have a big O of n to the second, and over here, I have a big O of n to the second plus 4n plus 20. Let's look at the difference between these guys. So when the size of the problem is 10, I have 100 over here and 160 over here. So it's almost like 60% difference. When the size is 50, I have 2500, and over here I have 2720. As you see, the difference is dropping drastically. And if I move on and make the size of the problem larger and larger and larger, you see these two are getting closer and closer and closer to each other, so that in this case it's not even 1% difference. That's why when we do the calculations and find a formula for big O of an algorithm, we usually go with the highest power of n, and we get rid of the lower powers, and especially the constant. So basically, in our word, in C++ programming word, we say big O of n2 is equal to the big O of this one. So we consider both of them to be n2. So when you're doing your problem solvings and taking care of exercises, consider that we're always looking for the highest power of n, and we get rid of all the constants. This table shows some common big O functions that appear in the algorithm analysis. So we have the constant, which the growth rate is constant. We have the log2 of n. This is when the growth rate is log2 of n. And because the algorithm function grows slowly, the growth rate of function f is very slow, and this is a fast algorithm. We have n, which we have it when the growth rate is linear, and it's directly proportional to the size of the problem. So as problem grows, the big O grows. We have n log 2 of n, which the growth rate is faster than the linear algorithm. We have n to the second, which the growth rate of this type of function increases rapidly with the size of the problem. And then we have the exponential one, which is 2 to the n, which the growth rate is squared when the problem size is doubled. This is the fastest growth rate of the problem size amongst all the algorithm. And as you remember, we had those over here. Let me just go back to that slide over here, and we looked at them prior to this on the graph. So you can see we have the linear in the middle, log 2 of n down here, n log 2 of n, 2 to the n, and n2 all together over there. We can definitely use big O notation to compare sequential and binary search algorithms. So if you look at it for the sequential algorithm, as we decided before, the big O notation says O of n because it was half of n for successful search. For unsuccessful search also it was big O of n, so that's going to be linear for sequential search, meaning when the size of the problem grows, the performance of this algorithm is going to drop in a linear relation. So for the binary search, we said for successful and unsuccessful search, we had log 2 of n. Remember, one was log 2 of n, the other one was log 2 of n minus 3. But as I just explained, we can ignore that minus 3 because that's a constant. And when the size of the problem grows, this basically is not um, doing anything. So we can just ignore it because those two are going to get together when the size of the program grows. So in both situations, we have log 2 of n, that if we go back to the graph that we had, we're basically comparing this line with this line. So now you can see how much more effective is binary search in comparison with the linear search. So this is not going to even go close to that linear line as the size of the problem grows. Okay, now it's time to talk about lower bound on comparison-based search algorithms. Sequential and binary search algorithms search the list by comparing the target element with the list element. For this reason, these algorithms are called comparison-based search algorithms. Earlier sections of this video showed you that a sequential search is of the order of n and a binary search is of the order of log 2 of n, where n is the size of the list or problem. There is an obvious question. Can we devise a search algorithm that has an order less than log 2 of n? Before we answer this question, first we obtain the lower bound on the number of comparisons for the comparison-based search algorithms. The theorem says, let L be a list of size n greater than 1. Suppose that the element L are sorted. If SRH of M denotes the minimum number of comparisons needed, in the worst case, by using a comparison-based algorithm to recognize whether an element X is in L, then SRH of n is greater than log 2 of n plus 1. The binary search algorithm is an optimal worst-case algorithm for solving search problems by the comparison method. From these results, it follows that if we want to design a search algorithm that is of an order less than log 2 of n, then it cannot be comparison-based. It's impossible because we need at least that many comparisons to find our result. We finished this video here. That's about the search algorithms. The next video after this will be about sorting algorithms. So go ahead and go to that video and to follow the rest over there. Thank you for watching, and this concludes this video.